All right, 3.2, the most important section in the book. This is all about measures of what we say is variation. So these are statistics that measure how much the data varies. We're not looking at the center so much as the spread. Think of it that way. And our idea here are calculate, interpret, and hopefully understand what these statistics tell us. So let's start off by looking at a picture here. We have two sets of data. There is one on top and then one just below that. And we're looking at these two sets and comparing the centers. Now, if you look at the mean and the median and the mode of these, this value, 100, will be the same. Okay, they'll have the same middle value. They'll have the same average. They'll have the same mode. This will be the most popular. Okay, they're all leading to 100. The only one that will be different will, no, actually even the mid-range will be the same, because if I add this plus this and divide by 2, I get 100. And if I add this number and divide by 2, actually it probably should be 85 and 125, I'll get 100. And if that weren't the case, you would just drag this over, right? Because 100 to 85 is what, 15? So technically I should only go up to here. But I could change these data values so that the mid-range would also be 100. Okay, so they all have the same center. But clearly, we can see that these two sets of data, this data and this data, are different. They're not the same, right? And this is what's getting at the idea of spread. So that's why we say, okay, we need somehow to show that the data varies, okay? And the statistic is then called the standard variation. First of all, the rule, the round-off rule, is the same as centers. So one more place value than what's given to you. All right. The simplest one that you've been introduced in the past has been the range. Okay, what is the range of the two numbers? Max minus the min. And you can see here, if I take the max minus the min, the range of this is much shorter than the range of this one. All right, so this is a simple one. It shows the overall spread of the data. It is not resistant to extreme values, meaning if you introduce numbers on either end of the spectrum, that changes the range quite a bit. And furthermore, it doesn't take into account all those values in between. Okay, because again, the range is only looking at the max and the min. So it's not too useful to us. It's an easy one to look at initially, but we need something more. And so standard deviation comes in the picture. And literally, what does standard deviation mean? It means how much do the data values deviate from the mean. All right, and we're going to arrive at a number, and that number is going to tell me how far, in general, are those items from the mean. So if I look back at this set, this here is going to have a small standard deviation, whereas this is going to have a large standard deviation, or I should say a larger standard deviation than the other, okay? Than the one above it. So when you compare standard deviations, it isn't like you look at a single standard deviation, but you compare two sets and look at how their standard deviations compare to each other, okay? All right. First of all, it's very popular, okay? You will see it show up in almost any type of statistical work. Second thing is that it's always positive. We never report standard deviations as negative values. Third, it is not resistant. meaning if you put in extreme values, again, and that's kind of bad news, it's going to fluctuate your standard deviation a lot. Finally, I think kind of the worst news is that we have biased data. Unfortunately, we know that most of the time our standard deviation is, I think it's under, okay? But it will either over or underestimate. This is a symbol for the real standard deviation. And so that's what I'm going to introduce to you next, what are the symbols. But it looks like a little tomato or a bomb or something. I forget the name of it. It's in our textbook somewhere. I'm looking, I don't see it. All right, well, if I come across it, I'll tell you what the name of it is. So there we have. S, write that down, is the standard deviation from the sample. So remember, here's our sample, right? And then the omega, I think that's it, just came to be, bam, omega. I believe that's omega. Omega refers to the standard deviation from everything, all right? So all of the stuff here. All right. Here's the formula. Here's how you calculate standard deviation. You probably want to write this down. And I should have, for example, x sub I. So you're going to take each individual item, subtract it from the mean, then you square the result of that subtraction. You add all those squares up. Then we take the square root of, we need to divide by n minus 1. That's a little bit of a mystery to me at this point. Why isn't it just n, for example? And I can explain a little bit about that, but not a whole lot. There is another way to calculate it. This is what's known as the common form. Machines and calculators and software programs typically use this formula, and this works as well. So it's something you could do and perfect it. We can get an approximation, by the way, like, did I do my work right? Just take the max minus the min, divide that by 4. You should get a number roughly close to your standard deviation. All right? So the ones I think important to have in your notes would be this one, and then obviously that having that little shortcut. And I'm going to go through an example. Looking again at the airport speeds that we had reported earlier, and I forget, this is Verizon data. So we have my Verizon data. There are my data items, and the first thing I'm going to do is calculate the mean. So we just add those up, divide by n, we get a mean of 30.74. All right, x bar. And notice our formula uses x bar extensively. All right, next thing, I'm going to go over to a table now. I'm going to take each of those data items. Here they are, right? There's x1, x2, x3, x4, x5. I subtract each of them from x bar. Doing this in a spreadsheet or on your software is not too tough to do. Then squaring each of those results, right? And so this is in your textbook. If you want to open up your textbook, you can see it there. It's probably a good one to have copied down just as an example of how to do it. I'm going to grab my calculator now. You can hit pause at this point if you want to copy stuff. And 23.1 minus 30.74. I take that number and I square it. Notice all those numbers end up being positive numbers. Yes. And so here I get 7.64. Again, I don't need to worry about positive or negative, all right? So that's why I wrote up here, think absolute value. Okay, so each one of these, I'm taking the absolute value of it. And the reason is because I square it, I lose whether it's positive or negative. and then these numbers here, I'm going to now add them all up after I square them, right? And that's going to give me 1083.052. You can check me on the machine, but I think I did that right. Okay, next thing, we're going to go through and then take n, which in this case I believe is 5. Now, this is a ridiculous thing to do standard deviation on, right? We never do standard deviation on 5 things, unless, of course, it's the first time that you've ever done it and you're practicing doing it by hand. But you want to do, remember when we talked about that, if I do statistics, I want to do it on n equals large, not 5. So what was that number? 1083? 1083.052. Okay. So I take that number, divided by 4, take the square root of that result, and that's going to give me 16.454878. And using my rounding rules, I report that as 16.5 megabytes per second. So this is the Verizon standard deviation. Again, it's a sample. It's not omega. It's not the full thing, right? Here then is how you interpret. What does that number mean, 16.5? And I'll come back to that in just a picture of that in a moment. Well, okay. Actually, it may help the next part for me just to draw it out. So why don't we go right below here. There's some space. So my mean is 30.74. So this is the average, think average, right, of my data set. And we have a normal distribution. We don't have a normal distribution, and we'll talk more about this in the future. It's actually probably irregular, but what the standard deviation allows me to do is think about if it were normal. And so it says, if I go out 16 this way, and if I add 16.5 to 30, I get something like 47 something and change. I'll just say ish. And if I subtract 16.5 from that, I get like 15 or, yeah, 15, 16.2 maybe? No, 14.2. All right? So if I look at my data set from here to here, in that region, I will have, and this is always true for one standard deviation to the left and right, I will have 68, I always forget, yep, 68% of my data. Now I can go out an additional standard deviation to 2 standard deviations out, and that would be then add another 16.5 to that, and that would be 50, 63-ish. Yeah. And if I go down here another 16, I'm going to actually go to a negative value, which doesn't make sense. So if I go down to 0, okay? Again, technically, if there was space, it would be -2 or whatever. Then in this region that I have now shaded, I'm going to do it in like a pink all the way through, from the 2 standard deviations, right? Now I have, and I have a nice little picture for this, so you don't have to copy this down, just look at this. Now I have 95% of the data are within 2 standard deviations. All right, so again, it tells me how far away the data is spread. The smaller the standard deviation, the tighter the data is around your mean. The larger your standard deviation, the more flat the data becomes. It gets spread out. All right, so here's a little chart. It's in your book. You'll see it from time to time. There's actually different pictures of it around the room. Here again, most of the data, 68% are sitting right here, right? There's the mean, And then this is 1 standard deviation to the left and right. 2 standard deviations to the left and the right. Once you get to 3 standard deviations, you're at 99.9% of the data that lives in this region. And it's probably not symmetrical, because data rarely is symmetrical, but it's roughly symmetrical. Okay? All right. So what they're telling us here is that if you are looking at significant data, okay, that you should be within plus or minus 2 standard deviations of the mean. All right? That would be what we would label as significant data. And there I have those 2 little stats. And I would suggest this is, maybe I should color this orange because it's something you should have in your chart. You should know this. Okay? They're going to ask you questions about it. It's not orange, is it? There we go. And sometime we'll get to more on this information in the future. So, all right. You have high significance if you are above 2 standard deviations. All right, so if you're beyond 2 standard deviations, if it's x bar plus or minus 2 standard deviations. So again, we always compare to the mean. So if I go 38 plus 2 times 16.45, I don't know why I did 16.45. Wasn't it just 16 and a half? Yeah, 16 and a half. 16.5. And that should be 16.5. All right. Now this one turns to 0 because if you do 2 times 16, you get 32, and 30 minus 32 is less than 0. And we can't have numbers less than 0 megabytes of download. It's not like they're sucking data out of your phone. That'd be hilarious. But above 63.5. So anything that's above 63.6 or below 0 would be considered very significant. So most of the data will be between there. All right, and that's what I'm saying here. But again, n equals 5. This is poor analysis because, again, I've only got 5 data items. If, however, big idea here, if I know the true population and I have the data on that, if I've collected all the data, then this is how you would calculate omega. Now notice here, my denominator is not n minus 1, but just capital N. All right? And again, there we have the true mean, not the sample mean, right? And again, that should be xi, not x1. All right. So very similar calculation, except we don't have to account. All right, variance. The variance is our third, and it is related to the standard deviation. How is it related? It is, you either square, so you're undoing the square root, right? We're getting rid of this. So we take the square of the measure of the sample standard deviation or the population standard deviation, which again we call omega. You square it, that's called the variance. And because, for example, in the last problem, we would have megabytes per second squared. And that unit is tricky to work with, right? So early on in our course here, we don't use the variance much. But the good news is this is unbiased, okay? So it's similar to that, but it's unbiased, so that's why we look at it, because it isn't like off as much. All right. Strange, huh? All right, couple properties there. So there's variance, standard deviation, huge idea, and range. Okay. And I think that's it. Yeah. We'll go on to 3.3 on Friday. Hopefully that makes sense and helps you work on the homework problems. Best of luck.